Thank you, and thank you so much for inviting me, and I'm sorry for not being able to be there with you. And also thanks for the previous speakers today who already mentioned a bit about the type 1a progenitor problem and about double white dwarfs in general. So in this talk, I'm going to focus on the type 1a supernova progenitor problem and on its implications to gravitational waves observations. Okay, so let's start with basics. Type 1a supernovae are important. They are a major source of heavy elements in the universe. And we also use them as standard candles in order to estimate distances. And this is how dark energy and the accelerated expansion of the universe have been discovered. However, despite their importance, nobody knows exactly what is exploding and how. And this is the so-called type 1a supernova progenitor problem. Now, until a couple of decades ago or so, the leading scenario to a type 1a explosion was the single degenerate, where we have a binary consisting of a white dwarf and a non-degenerate companion. And this companion can be either a main sequence star, a subgiant, a red giant, or a helium star. The white dwarf accretes mass from the companion until it reaches the Chandrasekhar limit and explodes. Now, in the past couple of decades, the double degenerate scenario has been gaining momentum. And in this scenario, we have two white dwarfs, a binary consisting of two white dwarfs, and they lose energy and angular momentum to gravitational wave, spiral in, and eventually potentially explode. So if we want to summarize, like in general terms, what are the main suggestions for type 1a explosions, we have one question. We have what is the companion? Is it a non-degenerate star or another white dwarf? And we can also ask what is the exploding mass? Is it a Chandrasekhar or even super Chandrasekhar, or maybe sub-Chandrasekhar mass, the total mass of the system? In the case of a Chandrasekhar explosion, we expect a delayed detonation that happens even hundreds of years after it reaches the Chandrasekhar limit. While in the sub-Chandrasekhar models, we expect a prompt double detonation where we have first detonation of the helium in the shell of the white dwarf, and then it triggers a detonation of the carbon in the core of the white dwarf. So in this case, we will expect the explosion to happen right after the actual merger. So if we look at the GW frequency of a binary, you can see that it depends on the orbital period, which in terms using the Kepler equation depends on the orbital separation and the masses of the components. Now, in the case of a single degenerate system, this separation at contact should be larger than about one solar radius, and even like tens of solar radii. While in the double degenerate scenario, at contact, we expect a separation of about 0.02 solar radius. So in principle, the GW signal of a double white dwarf merger should be around the decihertz band. And this can provide some potential for multi-messenger confirmation of the double degenerate channel if indeed we have a prompt detonation after the merger. So we observe the merger in the gravitational waves, and then right afterwards we see the explosion in the electromagnetic spectrum. And this can give us some clues about the nature of the companion and the explosion mechanism, and maybe confirm or rule out some of the channels. Now, the problem is we have two problems. One, here you can see a sensitivity strain plot as a function of frequency from a recent paper by Kinugawa et al. And here they show you the in-spiral signal of two different double white dwarf, equal mass double white dwarf. These are the dotted lines that you see here. So we have a double white dwarf with two masses of 1 solar mass and 0.8 solar mass and 0.6 solar mass, and they put it at a distance of 11 megaparsec because they estimate that at this distance we expect a type 1a rate of about 1 supernova per year. So if you want to have a chance for at least 1 supernova per year, we need to be sensitive to a distance of 11 megaparsec. And in this range, you can see that the sensitivity that we need is actually should be about 10 to the minus 20 in these units. While this is below, here you can see the sensitivity plot of LISA in green, and you can see that this is the merging itself is below the LISA sensitivity, while it should be above the sensitivity of those proposed experiments. And we'll come back to that in the next slide. And another thing you should see from here, this diamond, triangle, and circle mark different times before merger. So the circle is the merging time, the triangle is 3 years before merger, and then the diamond is 10 years before merger. So as was mentioned in the previous talk, we can actually see the signal of the double white dwarf years before the merger, and we can measure the system parameters, and we can localize it and get prepared for the multi-messenger observation of the explosion. So this is a good thing, but you can see that in this case here, all these mergers occur before at a frequency which is below actually 1 decihertz. So if we talk about the lunar gravitational wave antenna, you can see that this is the LISA sensitivity curve. Only above 1 decihertz, we get a better sensitivity than that of LISA. So if I go back to the previous slide, it means that this merger at this distance of 11 megaparsec will actually, we won't be able to detect them with the LGWA. And what the distance, the separation of the double white dwarf at contact depends on the component masses because of the mass radius relation of white dwarfs. So here I show you an example for the expected gravitational wave frequency at contact of different combinations of 2 white dwarfs. Here I assumed a carbon-oxygen white dwarf with hydrogen layers. And you can see that everything that is above the red line has a frequency larger than 0.1 hertz. So actually anything that is below the red line, all these combinations of masses, won't be, LGWL won't be sensitive to them. So it could only see those very massive mergers with combinations of, let's say, 1 solar mass and the 1 solar mass white dwarf. And the problem is that these combinations should be rare because of what we know currently about the mass distribution of white dwarfs. And also recent simulations show that super Chandrasekhar explosion, super Chandrasekhar mergers of white dwarf actually are not expected to produce normal type 1a explosion. So if these are indeed our sensitivity curves, we actually cannot see those mergers that will end up as potentially as a normal 1a explosion. So this is something to think about. Now I'm an observer, and from an observer point of view, what we want to do with the observation that we can do today is to try and see and characterize the local double white dwarf population. And by local, I mean like in the next a few hundreds of parsecs, and see what we can say about the binary fraction and the separation distribution of this population today. So if the double degenerate scenario is the leading channel to type 1a explosion, when we look at the population of present-day double white dwarf, we expect to see enough closed double white dwarf systems in order to reproduce the type 1a rate in the Milky Way. So one way to do it is using radial velocity variations. We take a large spectroscopic sample of white dwarf, where each white dwarf was observed at least twice, and then we look for radial velocity variations between the epochs. And this is what Badenes and Maoz have done back in 2012. They took a sample of 4,000 white dwarf from the SDSS, and they looked for radial velocity variations in each system. And then they plotted this distribution of delta RV max. Delta RV max is the maximal observed radial velocity difference per system. And you can see that this distribution composed of core. It has a very large core, goes up to 250 kilometers per second. Now, systems that are in the core of the distribution could be either binaries or single stars with just large measurement error, while systems that are in the tail of the distributions are very likely to be real double white dwarfs. And then what they did, they wanted to simulate a population of double white dwarf and try to get the synthetic delta RV max distribution and compare it to the observed one. In order to simulate the population, they draw the primary and secondary mass. The primary mass is drawn from the observed mass distributions of white dwarf. The secondary mass is drawn from a power law. And the separation distribution is drawn from another power law with an index alpha. And this is the separation distribution of white dwarf at birth after the last common envelope phase. And another parameter in this simulation is F-bin, which is the binary fraction of all white dwarfs within the orbital separation to which the data are sensitive. And then for each simulated system, they get the theoretical radial velocity curve. They sample it according to a sampling sequence drawn from the actual observed sample, assign it a measurement error, and then they have the simulated delta RV max measured for these simulated systems. They repeated it many times for many systems, and then they got these theoretical delta RV max distributions that you can see here in colored lines. And it turns out that the shape of the distribution is governed by F-bin, which is the binary fraction, and alpha, which is again the index of the power law of the separation distribution. And if when they checked it for different combinations of alpha and F-bin, they got these 1 and 2 sigma contours that you can see here. And the solid lines are of constant merger rate. And what they got is that the double white dwarf merger rate is actually very similar to the type 1a rate in the Milky Way. But the problem was that because of the high uncertainty of the SDSS sample, these numbers were highly uncertain. So we repeated the experiment with the SPICE sample that was mentioned in one of the previous talks. The SPICE sample is the ESO-VLT supernova 1A progenitor survey. It was a large program that was carried out 20 years ago by Napivotsky et al. With UVS and the VLT. They got high resolution, high signal to noise, multi-epoch spectra for about 800 white dwarfs. And this time you can see the spectrum of a typical white dwarf from SPICE.
Sorry,
yes?
We have a technical problem in this second with our screen. Can you just wait a minute?
Sure.
We have to solve a problem here, but it's not on your side, it's us.
Okay.
Okay, you're back again. Sorry for that.
Okay, thank you. Thank you. So anyway, we repeated the same experiment with the SPICE survey, and this time, because of the high resolution of the UV spectrograph, we could use the NLTE core of the H alpha line. So this is a zoom in on the H alpha line, and you see that the line here has a very narrow core that we can use in order to get an accuracy of about 1 kilometer per second. And I should have mentioned that the problem with measuring radial velocities for white dwarfs is that they have very few spectral line, usually only hydrogen Balmer lines, and they are very broadened because of the high density of the white dwarfs. So usually it's very hard to measure precise radial velocities for white dwarf, and only with this high resolution spectra we can use the non-LTE core of the H alpha line in order to get a precision of about 1 kilometer per second. So we repeated the same experiment with SPI, and we got this delta RV max distribution that you can compare to the one from SDSS I showed you before. You can see that again we have a core which is the result of the measurement, or but this time it goes up only up to 10 kilometers per second compared to 250 kilometers per second for the SDSS sample, and all the systems in the tail of the distributions are double white dwarf candidates. Now, when we combine the results from both survey, the SDSS and SPI, we got this. So these again are 1 and 2 sigma contours in the plane of alpha, which is the index of the power law of the separation distribution, and FB, which is the binary fraction, in this case up to 4 AU. So this is the binary fractions of white dwarfs with separations of up to 4 AU. In blue, you see the SDSS results. In green, the results from SPI, and red are the combined contours. And the solid lines are again of constant merger rate. And the dashed line over here, the red one, is the type 1a rate in the Milky Way. And you can see that the white dwarf merger rate that we measure is actually higher than the type 1a rate in the galaxy. And also by combining both surveys, we were able to pinpoint the alpha and S-bin parameters to a much narrower range. So if we focus on the combined contour, what we got is that about 10% of the white dwarf are double white dwarf with separations of up to 4 AU, and that about the white dwarf merger rate is between 4.5 to 7 times higher than the specific type 1a rate in the Milky Way. So it looks like there are enough double white dwarf mergers in order to account for the type 1a rate. But we are still not sure about the details. We don't know which double white dwarf end as type 1a explosions. And this is why we are following up now on these systems and trying to understand what are the mass distributions of component mass distributions and actual orbital separation distributions of the sample in order to say something more profound about the possibilities of these being type 1a progenitors. Now, what we wanted to do is to take these results and use them to predict what LISA will see. And the problem is that the current known sample of double white dwarf that you see here, these are all the known systems of double white dwarfs with full orbital solutions, is very small. We have only about 150 systems, and it's very biased. So here you can see the primary photometric primary mass as a function of period, and the highlighted region here is the LISA band. And you can see that we are biased to small periods of less than a day, but not very small ones. And these are the component masses. And you can see that most of the systems that we have come from the ELM survey, the extremely low mass white dwarf survey, which was very successful because we expect this kind of low mass white dwarf to exist only in binaries, because the universe the galaxy is too young for these white dwarfs to evolve from single stars. But these are not the general population double white dwarf. So this is why previous studies of the foreground and the detection of double white dwarf in LISA didn't use the known observed double white dwarfs. And binary population synthesis models predict between 12,000 to 25,000 detectable double wave dwarfs in LISA. So we wanted to take the previous results I've shown you about the binary refraction and the separation distribution and try to see what they imply for LISA. So the gravitational signal of a double wave dwarf has an amplitude that depends on the chirp mass, the frequency, and the distance. So what we did is to take the chirp mass and frequency based on the results I just showed you. And for the distance, we use the same assumption as in previous BPS-based studies. So the total number of double wave dwarfs in LISA should be the Milky Way disk volume, which we assumed using this profile, the wave dwarf number density, for which we use the 20 parsec number density of wave dwarf. And then we multiply it by the wave dwarf binary refraction inside the LISA band, which is about 10% using our results from SPI and SDSS. And this gives us about 2.6 10 to the 7 double wave dwarf in the galactic disk in the LISA frequency band. And now we want to see how many of them we will actually detect. So here you can see the characteristic strain plot of LISA. The solid line is the instrument noise. The dashed line is the default binary population synthesis driven unresolved foreground. And you can see that the orange solid line that you can see here is actually has a different shape. And this one, the orange line, is what we get using our observationally driven estimates. So we get a different shape for the foreground, and also we have a different number of detections. So these are the individually resolved systems, the gray dots over here, with a signal to noise ratio larger than 5 after 4 years of mission. And these are the underlying distribution. So we have here the orbital distribution, the frequency, chirp mass, and distance. The solid lines are the simulated underlying distributions, and the highlighted regions are the ones of the resolved systems. And you can see that the resolved systems trace more or less the shape of the underlying distribution. And it looks like the main difference between the observationally driven and BPS-driven samples lies mainly in the chirp mass. So the chirp mass of the observationally driven sample tends to be higher on average, and we also have some higher frequency systems compared to the BPS-driven sample, and these are the main reasons for the different shape of the foreground. So it means that when we do these kinds of calculations, it affects everything. So the different foreground affects also our number of detections and also what we can do for other science cases of LISA in this case. And what we got is that about 60,000 resolved double wave dwarf should have an SNR larger than 7 after 4 years, which is between 2 to 5 times more than what BPS study predicts for LISA. We try to do some model variations for that, changing the mass distribution of the primary and the secondary. But the main difference was when we took the most extreme 1 sigma values for alpha and FB, and this gives us a difference of about plus minus 20%, but it looks robust. So changing the mass distribution changes the numbers of detections by a few percent, and at most by taking the 1 sigma values of alpha and FB, we get a difference of about 20%. So to summarize, sub-decihertz gravitational wave enable multi-messengers observations of type 1a explosions in case of double degenerate prompt detonation. But I should note that we should be sensitive to frequencies of about 0.05 hertz in order to see it. The double wave dwarf measure rate is higher, a few times higher than the specific type 1a rate in the Milky Way, which is promising for the double degenerate scenario. And when we use estimates that are based on observations, we get more resolved double wide dwarfs in the LISA band than binary population synthesis estimate. And we also get a significantly different confusion foreground for LISA. So with this, I'll conclude.
Thank you very much for this great talk. Are there any questions? So maybe I can start because I want to ask this before already, but now I ask you. So I assume that because supernova type 1a are used as standard candles, that there can only be, only one answer to what the progenitor is. So my argument is, if you have different types of progenitors, then they wouldn't be working as standard candles so well. Or is, that's my question. What is your opinion about this? If there can be.
Yeah, so it's a good question because we do use them as standard candles, but we don't really know how they work and what are their driving mechanisms. So yes, if for different channels we can maybe we need to standardize them in a different way. And also we know that there are a lot of subclasses of type 1a supernovae. So maybe we need to use only a specific subclass of them for as standard candles. So yes, it can have profound implications to the measuring of distances in the universe.
Okay. Yes. Thank you.
My comment would be that indeed we do expect different scenario producing type 1a. This type 1a, will they look different from the other is unclear, but in one way to look to this is all supernova, all type 1a explode when the white dwarf is 1.4 solar mass. How we get there is not really important, you see. So is that because the accrete matter get to 1.4 solar mass explode? Is that because it's merged? Because the merging process is when the two white dwarf is destroyed, create a sort of disk of accreting material on the more massive possibly, and then it will explode 1.4 solar mass at the same. So they may not be that different when they explode, even if they come from different paths.
But the problem is, as far as I know, currently modelers think that sub-Chandrasekhar explosions are the leading channel to type 1a explosions. So they might not be all of them in the same mass range. I mean, the super Chandra or Chandrasekhar explosions could actually not look like type 1a, normal type 1as. So that's a good question. If there is a broader mass range that explode as a 1a, are they really standardized candles?
Okay. There's another question.
Hello? Oh, yeah. Well, thank you so much for your presentation, Nama. And yes, just being part of a supernova group there in Israel, I can also comment that there are, apart from 1As, there are also supernova-like explosions called 91 BGs, 1A X's, 2008 HA-like explosions, and more. So there's like approximately 10 different classes, and they all are thought to come from double Dwarf mergers, which also could have different mass combinations. And the name of the game is actually to identify the observed classes of supernovae with the types of white dwarfs that are emerging. So that will be very, very useful to disentangle. But actually, I had a question to Naama. So the question was, like you showed that if you take a white dwarf, which is a likely 1A progenitor, it will be somewhat below the LGWM band. But if you take entirety of many double white dwarfs in the galaxy, for example, are there estimates for the background noise of the double white dwarf population and how large it will be and how important it will be for the LGWA?
So it's a very good question because what I showed in one of the previous slides, and I'll try to go back there, maybe this one, yes, is that only the most massive double white dwarfs should reach a frequency above decihertz. And we know that there are not a lot of massive white dwarfs. And actually, we argue that most of the massive white dwarf come from mergers. So in order to have a double white dwarf consisting of two very massive white dwarf, I'm not sure I think it's not a very common system, because assuming that for most of the massive white dwarf you need first to have a merger producing them, then here you need to have maybe two mergers. So we don't really know, but I assume that these are not very common systems.
Yeah, but just a part of that question that I asked was also like, imagine you have 100 or maybe 1,000 or maybe more of these LISA systems that would be observed by LISA, but they also tap on progenitors. They will be,
Yes.
each individual will be below the sensitivity curve of LGWA, but if you take 1,000 of them, they will add up. Square root of 1,000 is 30 times more, so they might be observable as a noise.
Yeah, maybe. I haven't done the calculation, but it's something to consider. Yes.
Right. Thank you so much.
Other questions? Then, if not, I want to make one comment. So indeed, if you look at this plot, so now when you take all the improvements into account, the LGWA curve intersects LISA more at 20 millihertz. So it has gotten a bit better in that frequency band. So maybe it's not quite that bad, but still marginal, maybe.
Okay, great. And these systems are interesting on their own, maybe not as type 1A progenitors, but because my focus of my talk was type 1As, I said that, but it will be interesting to see these mergers as well, of course.
Yes. Okay, then let's thank Naama again.
Thank you.